dropping this in, h to the n factorial, oops, I should have put a k here, should have put a k there, h to the n factorial x over h, choose n factorial z to n, right? The h and the n, or sorry, the h and the z have the same exponent, of course, these cancel, so you're just getting the old binomial theorem with an argument of hz inside of it. So this looks an awful lot like, well, so yeah, so this is the same as 1 plus hz to the n, right, to this power. 1 plus hz, not to the n, but to the power x over h is what I meant to say. X divided by h. So he said this is true and this is true. And that was enough to prove the whole thing, because if you looked at this function, it's the same as this product. Which is, of course, this product. I don't know, I realize I just said this, I'm just trying to see if I actually understood it. Just repeating myself to see if I have any idea what on earth is going on. You know how it is. But yeah, this is this product, but this is also the same as this series, right? Right, by the same arguments, yada yada yada. But like this is this, therefore this is x plus y to the k given h over k factorial z to the k, right? And it's also equal to this product. So a formula for, say, the nth coefficient of that series on the left would be given by whatever formula you might have for the nth coefficient of a product of series like this, which in our case is, you know, x to the, you could do nh plus n choose 1, x to the n minus 1, h y to the 1, h plus n choose 2, x to the n minus 2, h y to the 2, h, yada yada. Yeah. Alright, so it wasn't that bad. Well, if you know the answer, it's not bad. Yeah, I wasn't going to do more today, but these do look interesting. And I don't know how to do them. Oh, I did look at 37 before, so let's talk about that one. I can handle 37. 38, I'm not going to know. I don't think I'm familiar with that one. But 37 I'm pretty sure I can handle. So 37 I would not have gotten if I hadn't looked at the answer, but now that I see it, like these numbers out front, like there's a 2 on the second term and a 3 on the third term as a coefficient, you know? They're almost like powers. It's almost like someone used the power rule to get them. So that's a hint, I suppose. I think I'm going to be able to reconstruct this thing. It's got to be the derivative of some binomial thing, right? Like, if those numbers weren't there, if all you had was the alternating bit, is that 1 plus x? Like, let's see. Yeah, it's finite. That's my problem. I was going to say like 1 plus x to the negative n, but that doesn't feel quite right. I mean, could we just do this? Right? And plug in 1. So for instance, oh, at 1, yeah, at 1 you get 0. Of course, you're right on the boundary here. Like, you're right at the edge of the radius of convergence on this function, I'm pretty sure. But is that true? It's been a while since I checked it. Yeah, I don't know. I haven't looked at this in a long time. The absolute value of that would be 1, and this guy just cancels to give you x. This is, of course, I know this is super basic stuff, so anyway, the ends are gone, you're getting like this. So there's an extra term there, and there's an extra term here. So we're getting n minus k over k plus 1, evidently. Yep. Okay, and we're taking the absolute value of that. So yeah, I guess it didn't affect anything. Anyway, at 1, we're getting 0 is this alternating business, you know, like n choose 0 minus n choose 1 plus n choose 2, da 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 da. Like that. Agreed? Which I'm sure was like one of the first things we proved. Oh, he didn't have us do that. We did something similar. Yeah, we didn't actually prove that, but well, we kind of did, right? Because if you let r equal n here, yeah, if you let r equal n on the right hand side, you get something like n minus 1 choose n, which I presume is supposed to be 0, right? Although, what do you actually get if you use the formula? I never thought about this. You get something crazy? you're getting n minus 1 minus n. You're getting negative 1 factorial. Cool. Okay, well, anyway, those are my little side random thoughts. But my thought was you should probably differentiate this and an n will come out, right? So if you believe this formula, you could certainly take a derivative of this and you'll get, I guess you're getting a negative? Yeah, you are. Okay, well, other than the negative sign, on the inside here, we're getting like k x to the k minus 1, which we could reindex. We could rewrite this as, let's see, at 0 you sort of get 0. Like if you looked at this old term, there was probably a 1 there, right? Yeah, you get like 1 minus x plus n choose 2. Well, not x, but nx is what I should have said. So the first term now we're getting is n. But anyway, you could start at 1 if you want. And I guess, are we going to end it? Oh wait, I didn't want to start at 1. I actually want to I want to reindex and start at 0 again. So we're starting at 0, but the first term that you actually see is 1. So we're reindexing everything. You get something like this. And this is k plus 1, x to the k. And yeah, I just shifted everything back by 1, so this is now n minus 1. And since as a derivative, it's the same as this. Which again, I suppose you could plug, like here when we plug in 0, you're getting a negative for the first term, which we probably didn't want. Yeah, probably not. But we don't mind n choose 1 being the first term that we start with, but he wanted to be positive. So I'm going to multiply by negative here, and I'm getting this statement. And we got a negative to the k, and then we have k plus 1 as a factor, and you go from 0 to n minus 1. But this guy has not changed. This is still n in the numerator. And now if you plug in x equal 1, you're getting 0 equals well, they made a little point here. Like if n is 1, then yeah, this is just gone, and you're getting well, you're getting 0 to the 0, first of all. But if n is 1, back here, the derivative of this is negative 1. Right? So this formula, it's fine, but you get negative 1 equals the stuff. I'll come back to that. If n is not equal to 1, then when I plug in 1 here, I get 0, and 0 equals, yeah, we're probably done, right? Yeah, when you plug in n minus 1 here at the bottom, the last term you get is n choose n. And other than that, there's this extra term. It's like 1, 2, 3, all the way up to n. You can see that matches up at n minus 1. So we do get this junk, the formula that we're trying to prove here. So we get 0 if it's not equal to 1. If it is equal to 1, that's kind of strange. Oh, you're probably only getting 2 terms. Okay, good. On the right-hand side, if n is 1, I thought we would get negative 1. But on the right-hand side, oh, you don't even get 2 terms, do you? Because it was 1 minus x. Derivative is minus 1. And on the right we have actually this is true no matter what x is, right? On the right we'd still have like 0 to n. Well, I took a derivative, so I guess it's n minus 1 now. If you want to use this formula, you would have something like the 1 term. It's kind of strange. Of 1, choose. You'd have this. Yeah, wild stuff. So at 0, you're just getting 1, 1, 1. 1, choose 1. I guess you're getting some freaking nonsense. Did I miss a negative sign? Is that what happened? Well, on the original function, you had 1 minus x, which of course at 1 is 0. I then took its derivative and I got negative 1. I wonder where I'm going with this. Maybe if I was a little more careful, it would have worked out correctly. We started with this. 1 minus x is 1 choose 0 minus 1 choose 1 times x to the 1, right? If we differentiate, you just get negative 1 equals negative 1 and all is right with the world? Oh, duh. Yeah, no. Of course for n equals 1 you just get 1 for this formula. Alright, cool. So yeah, there's 1 choose 1. If you multiply by negative. Yeah, it doesn't really have to do with the formula anymore. It doesn't really have to do with this function anymore. I mean, you can use the function again, but it's probably easier to just say, oh, look, that's 1. And we only have the 1 term. So 38, I don't know. 38, the question says, if you take, it's sort of like the same thing, but with a harmonic series. So I'd imagine it involves integrating. That would be nice, but I don't know. Equals partial sum of a harmonic series. That's what we're trying to prove. I don't know it. Well, I think I did look at the answer last week, but I don't remember it. I didn't really spend any time on it. But obviously, if you integrate, if you use the power rule, we have something like that, right? So, are we able to? Would I be able to just take this and integrate it? I don't mean x, I mean so here I'll get 1, other than this first term, huh? What if I took, what is this, 1 plus x to the n, right? So what if I took 1 plus x to the n and subtract 1 off from it so that I don't have this term, and then I integrate? Right? So you're basically getting k equals 1 to n. So it does match up with our series a little closer. Then integrate. Alright, so suppose I integrate this. That is the same as this series. Let's start at 1 again. And choose k, 1 over k plus 1, x to the k plus 1. And it's alternating. So I can fix that by making this a negative, right? So instead we'll look at this guy. Fair enough. And then I guess we could integrate. Like I just want to plug in 1 effectively. So we could integrate from 0 to 1. This is continuous. Is that almost right? What happened to my 0 term? Oh, I got rid of it. Because now am I wishing it was there? Because at 1, it's something, like my thing is off. I don't care about the power, but I do care about this number. I had wanted n choose 1 to be the first thing you see. I don't like this negative sign. It seems to be off by 1. So is it the negative of this? Fine, whatever. And then, but this power is wrong. How did I screw up the power somehow? Yeah, it's off. It's off every time. Huh. by 1? Grr. I leave. Man, I'm gonna correct that. Oh, maybe I could scale it. Okay, what if I took this and divided by x? If I subtract 1 and then divide by x, you have a 1 here. You have an x here, which I integrate, and then it matches up. Okay. So this is now an improper integral, but whatevs. The subtracting 1 is a lot like ditching the 0th term, and then I scaled it back. Okay. Then I scaled it back, and then I integrated it. So we're still doing this, but now right, now these used to be x to the like k minus 1 before you integrated it. So it integrates out to be 1 over k. I imagine this is the same. I didn't actually change the sign. Getting something like that. Which is what we wanted. Or is it? No, you actually want this negative sign to be the other way around. I realize we can just negate that, but did I get it wrong? So this series is like 1 before the division by x. I mean, we had 1. Yeah, this is the first power of negative x times, isn't this times n though? Should look like that. So minus nx plus n choose 2 x squared minus da 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 da. And since this is a positive power, just a positive integer we're dealing with, we're going to end up stopping at negative 1 to the n, x to the n. So it's this that I'm saying, subtract 1 from this, and then divide by x, and you're getting, damn it. Okay, so we are going to negate it. We should negate it at the beginning, because I'm getting the wrong sign on, So we'll take the negative of this function. So we'll take like 1 minus x to the n over x. And if you integrate that, you shall get an extra negative sign, which will be just enough to change that, Alright, now it matches up finally. When I plug in 1, you get the first term, which is positive, n choose 1. Like I'm saying, this gives you n choose 1 minus half n choose 2